Everyone to another seminar of Physics Latam. Today we are very happy to have Professor Andrea Puhm giving a lecture on the black hole string correspondence. Andrea has been professor at the University of Amsterdam since last year. She earned her PhD in theoretical physics from IPTH Saclay in 2013 under the supervision of Joseph Pena. She previously held faculty and postdoctoral position at École Polytechnique, UC Santa Barbara, and Harvard University. Her research focused on celestial amplitudes, black hole physics, and ADS-CFT. She is a recipient of many awards, including the ERC Starting Grant from 2020 to 25, and the Black Hole Initiative Fellowship at Harvard from 2016 to 2019. Remember to raise your hand at any point if you have any question. Now I leave you with Andrea. Please go ahead.
Thank you very much for the kind introduction, and thanks a lot for the invitation. So in the next 2 hours, we're going to take a journey through a field that has a long history, dates back to the 80s, 90s. And there's some old results that I will review, and then some new results from the last couple of years. And the topic is what's called the correspondence principle between black holes and strings. And I encourage everyone to, just interrupt me with questions if something should be unclear. Okay, so let me set the stage. So what is this all about? So I'm going to talk about a correspondence between fundamental strings and black holes, which serves as a general framework for matching black holes and massive states of fundamental strings at a point where the physical properties, such as mass, entropy, temperature, smoothly agree with each other. And what's the important thing here is that it offers a statistical interpretation of the entropy area law formula for black holes in terms of the degeneracy of string states. And therefore, it presents us a window in the mysterious workings of gravity. So I'm going to introduce in this talk the two protagonists, which are black holes and strings, and then I'll describe in detail in what sense they can be viewed as describing the same system. Okay, so let's start very basic. What's a black hole? Well, there are many answers that you can give. One is it's a region in space-time where gravity is so strong that light can't escape. Since I'm talking about light and escaping, there's another answer that you could give. So while black holes themselves classically don't emit light, they have a accretion of matter around them, which does emit light. And black holes also emit other kinds of particles or waves, gravitational waves, when they move very fast. For example, if they encounter another black hole and they merge. And you can then give an answer that the black hole is what LIGO or the Event Horizon Telescope have observed. Another answer is that it's the endpoint of the gravitational collapse of a star. Yet another is that it's an object in general relativity with a horizon that cloaks a curvature singularity. Could also say it's a solution to Einstein's equations. And as a solution to the Einstein equations, it's given by a space-time metric that describes what are called Schwarzschild Kerr or Kerr-Newman black holes, depending on whether they are characterized by their mass or their angular momentum or their charge. Another answer could be that it is a playground for questions in quantum gravity. And this is the kind of setting in which I will discuss black holes. So the very simplest black hole is the black hole that's just determined in terms of its mass and 4 dimensions. It's given by the Schwarzschild metric. There are two notable features here. One is that at r equals 0, there is a curvature singularity where the transverse sphere shrinks to 0 size. At r equals 2 gm, where g is Newton's constant and m is the mass of the black hole, there is a coordinate singularity where the signs of the coefficients of the t squared and the r squared flip. And so as you go beyond the r equals 2 gm radius, the coordinate r becomes time-like, and so any particle that crosses the event horizon from the outside to the inside will continue to evolve towards smaller r until they approach the singularity. So it's the same as what happens when you're outside that you cannot prevent moving forward in time. And this surface is called the event horizon. There's also an interesting ultraviolet infrared relation, because there's gravitational redshift near the horizon of a black hole between the asymptotic region and that near horizon region. And then there are some interesting laws that black holes seem to satisfy. So these are so-called laws of black hole mechanics. And if you compare them to what happens in ordinary systems, when you look at how they behave thermodynamically, there are some striking similarities. So T on the one side is the temperature, which on the black hole side is given by something that is called the surface gravity. And then there's the first law of thermodynamics and the first law of black hole mechanics, from which one can extract some striking analogies, which lets us interpret the black hole as having an entropy given by the surface gravity, a temperature is given by the surface gravity, and an entropy given by its area, so the area of the event horizon. And then there are some important factors, numerical factors here. Now, black holes, when they have a temperature, they can emit radiation, and this happens through quantum effects. And so black holes are actually not stable objects once quantum effects are introduced, and they can actually evaporate. In this talk, we will not much dwell on what happens to black hole information as black holes evaporate. The main thing that we will talk about is the entropy of a black hole. So let's focus on that a little bit more. So the entropy of a black hole is given by the area of the event horizon divided by 4. But an entropy is a number, and the area is given in terms of some units, so length squared. And so I have to put back in here the length scales that I have previously omitted. So this would here be the Planck length squared, that's a natural length scale, which is related to the constants of nature, Newton's constant, h bar, speed of light in this way. And from now on, we will be working units where h bar and c is 1. And so we can write the entropy as the area over 4g. So that's the famous area entropy law. Now let's compare this to, let's look at a few entrophies of objects that we know. So for example, a black hole that has solar mass, mass of the order of our sun. This number would be something like 10 to the 78. There's also supermassive black holes in the universe, which have 10 to the 10 solar masses. And then this number would be something like 10 to the 96. Now, if we compare this to our sun, that has like 10 to the 60 as its entropy, or the entire universe without black holes would have something like 10 to the 87. So you can see the entropy of a black hole is a humongously large number, even more so the more massive the black hole is. And we would like to understand what this number actually means. So in the theory of general relativity, as I said before, we can describe black holes by some metrics. And they have very few parameters. They have the mass, the angular momentum, and the charge, but that's it. Now, if you interpret the entropy of a black hole thermodynamically, like we do for ordinary systems, then it looks like black holes are actually not very elementary. They're very complicated because they have e to the entropy number of microstates. So for example, one of these supermassive black holes, which was recently imaged by the Event Horizon Telescope collaboration. So that black hole has an entropy of 10 to the 95, whose exponential would be the number of microstates of this particular black hole. But in general relativity, we have only this one state given by its mass, angular momentum, and possibly charge. So this one in general relativity versus e to the 10 to the 95 begs for an explanation. And so this is the context for this talk. We would like to understand a sort of give an understanding of black hole entropy in terms of more microscopic terms. Now, in general relativity, this is not possible. There's only one state. So we need some theory beyond. So let's start with, again, simple. So when we have special relativity and we add quantum mechanics, we get quantum field theory. Very nice. But once we add to quantum mechanics general relativity, we are in the realm of quantum gravity. And we know that gravity as an effective field theory is not valid to arbitrarily high energies. And so there we need a new theory. And there is a proposal out there, which is string theory. So we're going to look at string theory and try to understand black holes in that context. So let me start again very basic. What's a string? Well, comparing it to particles. So particle follows a world line. A string follows a world sheet, is an extended object. It's the fundamental object of that theory. And it does two things for us. One important thing is that it smoothens out the ultraviolet divergences of quantum field theory by replacing the point particles by extended objects. And then there's another thing that it does, which comes by looking at what type of strings we can have. So we can have either closed strings or open strings, and open strings are such that at the endpoints, other fundamental objects can live. So those are called D-branes. And closed strings naturally furnish us what we call the graviton. So gravitons naturally come out of string theory. So that's the first connection here to black holes. Now, actually, if you take look at these D-branes, you can look at the theory living on a D-brane and you find some gauge theory, while these closed strings give you naturally gravitons or gravity. If you put the stack of branes together, then you can actually get spacetimes that look like black holes. So that's another way to see that there's some natural connection between strings or branes and black holes. And we're going to explore this further in this talk. But let me first go back to the fundamental string and discuss some of its properties like we just did for black holes. So for string, let's consider a closed string, a bosonic one, in general space-time dimensions. If you solve the equations of motion of that string, you will find this position operator for the string, which has some center of mass location, some linear momentum, and then a bunch of oscillators alpha that make the string wiggle. We're going to work in light cone gauge, so then I only have to focus on the transverse directions of the string. And we're going to introduce this so-called level counting operator. And we're going to note that the mass or squared of a string, as given by momentum squared, is related to this level counting operator in this way. Now I want to compute the entropy of a string, or the degeneracy of states. So I'm going to look at the partition function, which is given by trace of e to the minus beta n being the level counting operator, and beta being the inverse temperature. And if you plug in the formula from the previous slide, the right-hand side is the expression that you get. So there's this infinite product of 1 over 1 minus e to the minus beta n to the power of the transverse directions. Now, in the high temperature limit, this infinite sum simplifies. And the way to do this is by looking at the specific properties of the string, which are so-called modular transformation properties. And so in the infinite temperature or beta to 0 limit, the partition function just simplifies to this very simple expression. There's some exponential that involves 1 over beta, and then there's some factor with some powers of beta out front. Now, the density of states can be extracted from this infinite sum, which is the partition function. And the way to do this is to notice that this sum is dominated at large values of n. And so in order to extract this density of states, dn here, you can use a saddle point approximation. So there would be some integral over beta of some expression that involves this n. And if you take n large, you can use a saddle point approximation to evaluate that integral. The result is the following expression. So there are some powers of n, and then there's some exponential, which involves the square root of n. And this number here is the ways of applying alpha oscillators to the vacuum such that the mode numbers add up to n. And this actually dates back a long time ago. This is not supposed to be 2018, but the previous century. And this is a classic result from number theory due to Hardy and Ramanujan. Okay, so now we have the density of states of a string at excitation level n. And from that, we can then read off the entropy. If I forget about the prefactor, this is just given by the square root of n that comes from the exponent. And that is also proportional to m. And so this is a relation to keep in mind. The entropy is proportional to square root n, and that's proportional to the mass. Okay, so now we can address the question, why do we think that black holes and string have something to do with each other, and how can you understand their connection? So the point here is that a black hole is a highly massive, highly degenerate object. A string is a highly degenerate object. And we would like to give a microscopic interpretation of black holes in a theory where general relativity is no longer valid, but we have string theory. And so we would like to understand this area over 4 times Newton's constant in terms of some stringy or brainy degrees of freedom. And the goal will be to understand some connection, some microscopic understanding of this formula for Schwarzschild or Kerr-type black holes that are in spacetimes that are roughly flat when you go far away. So this would include black holes in our universe if you stay below scales where you don't notice that the universe is actually expanding. And we would also be interested in some higher dimensional cousins of these Schwarzschild and Kerr type black holes. And the point here is that we would like to get a microscopic understanding of black hole entropy in situations where we are in flat space, so no anti-de Sitter space. So no way that you can use the so-called anti-de Sitter conformal field theory correspondence. And we would like to understand this formula for black holes that are not supersymmetric or BPS. And this is a much harder question or problem to solve. So this would be the ultimate end goal. And if we're away from situations where you have supersymmetry, which usually gives us a lot of control, or you are away from situations where you have the ADS-CFT correspondence that gives you a sort of a well-defined setup for quantum gravity, then we don't expect to have enough power control to actually get all the numbers right. So this 1/4, for example, we don't expect to get right. And so in the following, we will actually drop order 1 numbers, unless they're important. And so you might call all of the equalities that will follow from now on as sort of wiggly mathematics. We're interested in understanding the scaling, and in particular, the entropy of a black hole is given by the area over G Newton without order 1 factors, because we are trying to do, this is a very challenging problem. There is no control from supersymmetry, or there's no sort of well controlled and well-defined framework like we have in an anti-de Sitter quantum gravity box. Okay. So the plan for the rest of the talk is to give more motivations for why black holes and strings should be related. And then there will be 2 parts. The first part reviews the correspondence for black holes and strings that are static. And I will highlight there some important details where you have to match properties of black holes and strings, including mass, decay rates, and sizes. And I will then describe in more detail in which sense there is a correspondence between black holes and strings, or a transition between the two. And that will, the important thing there will be to have as approximately adiabatic transition. And I will refer to this as Goldilocks adiabaticity regime. And then in the second part, I will go from the static correspondence to one where we include rotation. This will raise various puzzles. And we will resolve them. And then we will provide further evidence for a correspondence between black holes and string with rotation by looking at their sizes and shapes. Are there any questions at this point? Okay, if not, then I'll move on. Okay, so there's a various works dating back to the early 90s that this talk partially reviews, and here are the references for you for further reading. Okay, so let's come back to our 2 protagonists, black holes and strings, and let me take this moment to emphasize a very important aspect, which is that black holes and strings are usually discussed in different units. So for black holes, we have Planck units. So the Planck mass, the Planck length, they're related to Newton's constant G. And in D dimensions, there are some dimension-dependent exponents there. Strings, on the other hand, we usually describe in string units. So string mass, string length, or alpha prime. And there's a relation between these units, of course, which involve powers of the string coupling. And if you want to make comparisons between these 2 objects, we should, of course, always work in the same units. So this is to keep in mind. So then let's get back to our protagonist number 1, strings. So let me just highlight again a few points. So we have the string tension, which has this relation with the mass and the string length. The strength of the interactions from Newton's constant, or the gravitational interactions, relate these 2 length scales, the string and the Planck length, via the string coupling. And we can have the string coupling vary in space and time, and this is conveniently done by tuning the dilaton. And that will be actually something that we will come back to, because we will think of physical processes for varying values of the coupling across spatial regions of interest. And what we will do is we will think of sending a dilaton wave through our system that changes the value of the coupling. Then back to protagonist number 2, black holes. So now we upgrade from 4 space-time dimensions to D. The important thing here is the horizon radius, which gives us the area of the event horizon. And in D dimension, it's given by 1 over g times the mass to the power d minus 3. We can express this further by replacing Newton's constant by the Planck mass. Then we have the expression on the right-hand side. The curvature is given by, for example, the Riemann squared, the Kretschmann scalar, which is inversely proportional to the horizon size squared. So it's given by that expression on the right-hand side. And now, because I said before, we should be describing black holes and strings in the same units if we want to relate them. So let's go from Planck units to string units. Then we get those expressions. And here you notice the appearance of the string coupling. And so what we notice is that the curvature of the black hole increases as the coupling is reduced. And so this is already something that hints that there is a relation between black holes and strings, because as we tune down the coupling, the black hole will become smaller, and then at some point, stringy effects will come into play. So how does this work now? So let me first give some more motivation for the connection between black holes and strings. So I said before that they're both massive and highly degenerate. So they both have an entropy. So this one checks out. There's another reason why you might say there's some relation between black holes and strings, and that is that they obey some bound on their angular momentum. So for black holes, there's this Kerr bound. So I'm writing this now in 4 dimensions, but we will come back to general space-time dimensions later on. So in 4 dimensions, there's the Kerr bound, and no black holes exist above it. And this Kerr bound scales with mass squared. Now for the string, there's also a bound. It's called the Regge bound. And it says that no strings above the Regge bound, which is given by mass squared, exists. So it looks like we have another sort of analogy between black holes and strings due to the appearance of an angular momentum bound. Now let's get back to the entropy, which is the thing that we would like to match. So on the black hole side, we computed before, it's proportional to the area, which is proportional to the mass squared. On the string side, we have computed that as well. And we found that the entropy is proportional to the mass. So that doesn't seem to check out, because one is proportional to mass, the other one mass squared. Though now, the important comment that I made before comes in. You should mind the units. So on the left-hand side, we were using Planck units. On the right-hand side, we were using string units. Let's now compare them using the same units. Okay, so we have again these 2 bounds. We have the entropies in their respective units. And now let's take the black hole side and express it in terms of string units. So for the entropy, if you express now the Planck mass in terms of string mass units, then you actually see that the black hole entropy and the string entropy can agree at a certain value of the coupling. So when g squared is given by string mass over mass of the string, which is the so-called correspondence point, then the entropy of the black hole is equal to the entropy of the string. So that's great. So now we get an actual connection between black holes and strings. Now let's go back to the angular momentum bounds. And by the way, we can keep the coupling small and the entropy large and be in a regime where we have some sort of perturbative control. About the angular momentum bounds, yes?
Andrea, I have a question. This model that you are using for the string part is only bosonic, because you say you don't want to use SUSY.
I mean, the general story doesn't really matter what string you use. So before I started with the simplest setting, and indeed I will continue to use sort of the simplest string in order to make the connection. We will see that things, as we go on, we will see that things work much better than you might expect. Not just because you could, because this is the sort of the simplest string, but because of other reasons that I will get to. But then at the end of the day, you can refine your model and look at different kind of strings, also in different theories and so on. But for now, we don't need that. Okay, thank you. Okay, so now let's look at the angular momentum bound. So if I express the Kerr bound in string units, we actually see that the Kerr bound is much smaller than the Regge bound. As you can see, when we want to keep the entropy large to have a macroscopic system, and we can keep the string coupling small in doing so. And we see that the Kerr bound is much smaller than the Regge bound. And so that was actually not a good reason to say that strings and black holes are related, because the two bounds have nothing to do with each other. But we will get back to rotation as we go along. We actually have puzzles that come related to the fact that the Kerr bound and the Regge bound are very different. And the puzzles are the following. So it seems like that for strings between the Kerr bound and the Regge bound, there's actually no black hole counterpart. So there's nothing that the string could correspond to. And let me emphasize that this is really a puzzle. On the one hand, black holes that saturate the Kerr bound are still roundish kind of black holes that have a large degeneracy. But strings near the Regge bound, they're very thin, elongated. They're like rotating rods, and they're very small degeneracy. All the oscillators have to be used up in order to get angular momentum, and they cannot be used to make the string wiggle, which gives it its entropy. So these look like very different objects, and in between there doesn't seem to be a black hole matching onto the corresponding strings. In higher dimensions, there exist ultra-spinning black holes and also other black objects like black rings, where the angular momentum is much above the what we might call Kerr bound in higher dimensions. So there it's not an existence bound. There can be objects beyond the Kerr bound, and they can highly spin. But for strings, there's a limit up until the Regge bound. And so it seems like there are black holes or black rings which would not have a corresponding string counterpart. And so now you might say, well, if you add rotation to the game, then does the black hole string correspondence fail? And of course, the answer is no, otherwise I would not be giving this talk now. So actually, there are two puzzles. And in these two puzzles, there are assumptions hidden. And the assumption is that there is a one-to-one matching of stationary solutions. But we know that at finite coupling, nothing's really stationary. All these objects time evolve. And the important thing here is then to understand what timescales we're looking at. So what timescales, what are the timescales of instabilities of the objects, and what is the timescale in which we want to transition a black hole to a string or vice versa. And we have to compare them. And the puzzles that I just mentioned, they will then be resolved if we account for the fact that there is dynamics happening. Okay, so that was the motivation. I'm now going to go to describing in more detail the correspondence for black holes and strings in the absence of rotation. Okay, so here we have again black holes and strings, and these are works that date back to the early 90s, early mid-90s. Susskind, Horowitz-Bolczynski, Damour, Veneziano, and others have discussed this idea. And it starts with noting something that we stated before, which is that the curvature of a black hole is given by the inverse of the horizon radius squared, which I expressed now in string units. If the coupling gets decreased, we noted before that the curvature actually increases. And so at some point, there are stringy corrections to the black hole geometry that become important. And these corrections happen precisely at the so-called correspondence point. I have expressed before the correspondence points where the entropies of the two objects agreed in terms of masses. I now express it in terms of the entropy. And this correspondence point now happens at g square being 1 over of the order 1 over the entropy. And because we're looking at objects with large entropy, this is still very small. If we go further, decrease the coupling further, we enter a realm where we have like weakly coupled theory, and we can actually do string perturbation theory. And so as we move along this coupling from finite string coupling to smaller string coupling, where we started out with something that was well described by a geometry, then it receives stringy corrections and it becomes weakly coupled. This is sort of the picture that we have about the correspondence, starting out with black holes, decreasing the coupling, and then entering in a regime where they're described by strings. Conversely, we could start with a free string, then turn on the coupling, at some point, gravity will be important and the string will self-gravitate. And then it will cross this correspondence point. And beyond that, there will be a description in terms of a geometry, in terms of some geometric object. Now, what we were going to do in the following is we're going to take these two objects, we're going to take their entropies, and we're going to equate their entropies across the changes of the coupling. So entropy will be the thing that will be fixed across the coupling. Now, in one side of the regime, when G string is finite, we will have a description in terms of a black hole. On the other regime, where G becomes small, we have a description in terms of strings. As we approach the correspondence point from both sides, we can no longer describe the system either by a geometry or by a weakly coupled string. It will be something else. But we know that as we cross this correspondence point, at this location of the coupling, we have an interpretation of the Bekenstein-Hawking entropy formula for the black hole. On one side of the transition, we have a black hole with this entropy. On the other side of the transition, we have a fundamental string with that entropy. And the two descriptions collide at the correspondence point and therefore furnish a statistical interpretation of Bekenstein-Hawking entropy. And I've said this in 4 dimensions, while in D dimensions, the only change is that there is a power, various powers of space-time dimension that get sprinkled over these expressions. So let's look at this in a little bit more detail. So what I said was that fixing the entropy is what we're going to do, and then we're going to change the coupling. And so in this picture, there is a dimensionless parameter, which is naturally given not just by the coupling, but by the coupling squared times the entropy. And this parameter you might call a 't Hooft coupling. Why is that? So it changes how the object is described. At G square S much bigger than 1, it's well described by a black hole. At G square S much smaller than 1, it's well described by a fundamental string. And as we approach the correspondence point, which is at G square S of order 1, neither one is really a good description. But as we cross this correspondence point, we enter again a description that is either described by a string or by a black hole. Now, let's compare this to our usual favorite quantum gravity framework, which is the anti-de Sitter conformal field theory correspondence. There's a similar parameter in the gauge theory, lambda given by G Young-Mills squared times n. That's a 't Hooft coupling. Or there's another similar dimensionless parameter in D-brane systems, where it's given by G times n, the number of the D-branes. And so this G square S, for the purpose of completely general black holes in arbitrary dimensions, this plays a kind of similar role as these other two coupling parameters. What is not known here is whether there's any dual gauge theory in which this G square S is really what we would call the 't Hooft coupling of a gauge theory. So that's an open question, but this quantity shares similar features with the 't Hooft coupling in ADS-CFT or the effective coupling in D-brane systems. Now, since I mentioned these other instances of where we have a 't Hooft coupling, and since I mentioned D-brane systems, let me first, before discussing the black hole string correspondence for generic black holes in asymptotically flat space, let me go first to the realm where we understand things very well and where we have control. And this is where we have supersymmetry. So one of the great successes of string theory has been to give a microscopic interpretation of black hole entropy in terms of strings and D-branes. And this is in the regime where we're looking at special kinds of black holes that are supersymmetric or BPS, which are black holes that have a certain relation between their parameters, mass, and the charges and angular momentum. And when there's supersymmetry, then there are certain quantities that are protected as you change the coupling. So what we're going to do here is we're going to fix the number of branes, and we're going to count the number of ground states at 0 coupling. And this turns out to be a quantity that is protected as we change the coupling. And so once we have a microscopic interpretation for the system, we can use the answer that we get from this computation as we change the coupling. So if on the one side we have a black hole that is supersymmetric, described by a number of charges. So I've chosen here sort of the poster child black hole, which has 3 charges given by Q1, Q5, and Qp. And this is a good description. The black hole is a good description in the regime where G times the number of the branes, it's much bigger than 1. On the other hand, when G times n is much smaller than 1, then there's another system described by 3 charges associated to the charges of D1 and D5 branes and momentum. And there are D branes with open strings on top. And we can count the degeneracy of their ground states given by these numbers N1 and 5 and the NP. And one can see that the entropy of the black hole computed in the black hole regime and the entropy of that deep bound state of D branes computed in the weakly coupled regime, they perfectly match. And so this is one instance where we can really also match order 1 numbers across changing values of the coupling. Now, if we go away from supersymmetry, away from BPS, and we excite the system a little bit, then we have, on the one hand, a black hole that is no longer BPS, but it still sort of satisfies some extremality, near extremality conditions, so it's close to extremality. On the other hand, the weakly coupled system is near BPS, near supersymmetric. And there's still some way in which we can describe this system, and we can compare them. If we go far away from BPS, so far away from extremality, then this is no longer the case. We no longer have a protection of the quantity that we computed before, the degeneracy of states. There will be some renormalization, and this quantity will just not be the same as we change the coupling. However, in the context of this black hole string transition, we can still get a parametric matching. But now there will no longer be equal signs with numbers, but there will be wiggly signs. And the important thing to notice here is that we are beyond the regime of the anti-de Sitter conformal field theory correspondence because we are far away from extremality. And we no longer have supersymmetry to help us out. And this is the kind of setting that we're going to be in from now on. Okay, so once the black hole then becomes completely neutral, there are no more extra charges sprinkled on top, then we are really in the framework of the black hole string correspondence as proposed by Horowitz and Polchinski in '96. And this is where we have a priori no control, and there will be renormalization across the change of coupling. So to summarize this, I advocated that this parameter G square S is kind of like a Toft coupling that lets us label in which description we are. So if it's much bigger than 1 black hole, much smaller than 1 string of order 1, then it's something in between. And this is mimicked by black holes and strings and branes when we are close to supersymmetry. And the relation between them is that in there, we are in a setting where we really know what the microstates of a black hole are. So we know the number of D-brane states. And so what we do there is we fix n. So then the parameter there is G times n. Now, in the case where we're away from supersymmetry and away from any sort of control, we don't have n. We don't know what n is, but we still have the entropy. And so the entropy in the BPS case is given by n. And so once we are away from supersymmetry, we don't have n, but we still have s, so we're going to fix s across the correspondence. So this is sort of the natural quantity to look at. And so then the black hole string correspondence is an overarching framework that allows us some microscopic understanding of black holes in string theory, and in particular, the entropy area law formula. And the idea is to interpolate between these two descriptions by changing the coupling. And this has to be done almost adiabatically, otherwise we can't say that we are looking at the same system. And while changing the coupling, there are some quantities that we want to keep fixed. One is the entropy, because we want to compare the same system. And there are also some other parameters that we might want to keep fixed, which are the angular momentum and the charge. Now, in general, properties of either black holes or strings do not stay the same across the change of coupling. So for example, the mass of the string and the mass of the black hole will change. There's some renormalization, and this is in general hard to control, unless you're in a situation where you have supersymmetry, and you're allowed some more precise statements across changing the coupling. Now, there are some details of the correspondence that we have to talk about. So we're going to fix the entropy, but then we have to see whether the properties of strings and black holes agree at the correspondence point. Because if they don't agree where the black hole and string should go into each other, then we don't have any correspondence, obviously. So some properties that we want to match are the mass, the size, decay rates, because neither string nor black hole will be eternal. They will evolve. And so also the decay rate should match at the correspondence point. And we can really only talk about the correspondence if the transition between the black hole and the string happens almost adiabatically. And we will talk about that. And then we would also like to have a sort of physical realization of how you can actually go between a black hole and a string and back. Okay, so let's get to the matching of properties between black holes and strings as we approach the correspondence point. So the first one is the mass. If we fix the entropy and we vary the coupling, before we saw that mass, entropy, and coupling are related. So the entropy is given in terms of the mass and the coupling. So if we fix it and we vary the coupling, then the mass has to change as well. So the mass gets renormalized. On the string side, these are some order G-square corrections. So it's roughly constant. On the black hole side, there is some serious renormalization going on. And we can just depict this in this picture where we are drawing adiabats. So on the string side, the entropy stays roughly constant as we approach the correspondence point. But on the black hole side, it changes quite a bit. But you can see by plugging in the correspondence point value for the coupling, which is G-square being 1/s, that the two masses actually agree. So that is a consistency check. We have fixed the entropy, the mass changes, but it agrees at the correspondence point. So that's the first check that strings and black holes can describe the same physics. The second point on the list is the size. So we started out with a large black hole, then we decreased the coupling. Black hole becomes smaller, the curvature becomes larger, and at some point it should go over into a string. However, when should it go over into a string? Well, the black hole will have the size of a string at the correspondence point. And now we have to compare that size to the size of a string as we approach the correspondence point. Well, the size of a string, you can model it very easily by some sort of random walk. So the string does some random walk, and you can estimate from that the size of the string. Well, that is given by square root of the entropy times the string length. And so this, for a large entropy, is much bigger than the string length. And so we seem to have a puzzle that at the correspondence point, the black hole is of string size, but the string itself is much more fluffy. But there's a way out, and the way out is that we have actually neglected an important effect, and that is the effect of self-gravity. While a weakly coupled string does a random walk and is very fluffy, once self-gravity kicks in, the string actually becomes much more compact. And this will shrink the size of the string. And this is has been understood in a famous paper by Horowitz and Polchinski, which is not the same as the one as I mentioned before. So they wrote a second paper where they explain how the sizes across the correspondence can match. And this is due to the effect of self-gravitation. Self-gravitation will not play a role for the rest of the talk, but it is important to keep in mind that when we actually want to match properties across the correspondence, then this is an important effect. And as we have seen here, in certain instances, it's necessary to get a matching. Okay, so next we're going to talk about dynamics. So once we're away from zero or infinite coupling, neither strings nor black holes are stationary. So there are self-interactions of a massive string, which makes it decay. And there are two major decay channels. One is the string can fragment into smaller strings, or it can emit light strings. Black holes are also not stationary anymore once we include quantum effects, as we have discussed before. And so they can evaporate via emission of Hawking radiation. So neither of these objects are stable, absolutely stable. And so there's some decay rate that we can compute for them. And they also have to match across the correspondence. So this is the picture for the decay rates as a function of the coupling. And the red line here, which is at the value of chi square being of order 1/s, that marks the transition between string and black hole. So away from these stationary points, the coupling, the decay rate will vary with the coupling. But then at the correspondence point, you can see that these two decay rates of the string and the black hole, again, match. So that's another check that strings and black holes can describe the same system. Now we have to talk about the transition itself. So the transition has to be approximately adiabatic from string to black hole or back, because otherwise we don't describe the same system. So let me explain this in more detail. So we want the rate of change is what we have to look at. And if we describe the string coupling by the dilaton, then it's the change of the dilaton. The rate of change has to be slow enough such that the state doesn't get excited. Because when it gets excited, then the entropy changes, and then we're no longer keeping the entropy fixed. So we're no longer describing the same system. In order to have a slow enough rate of change, we can achieve this by having a dilaton with long enough wavelength. When the dilaton wave goes through the system, that means the coupling changes, but it should be slow enough or have long enough wavelength while doing so. On the other hand, the rate of change should also be fast enough such that the entropy stays constant. Because, for example, the black hole, if it has long enough time, it will evaporate a lot of its mass and therefore its entropy away. And we want that change in entropy to be very small. So there's a regime based on these two conditions in which we can sensibly talk about a black hole string correspondence. I will refer to this as the Goldilocks adiabaticity regime. So the rate of change of the coupling should be not too slow and not too fast, and it should be within these two bounds. 1 over the string length and 1 over the entropy times the string length. Now, where does this come from? So at the correspondence point, the system, after we include self-gravity, is of the string length size. A long enough wavelength is needed not to excite it, which means that the rate of change, the inverse rate of change, should be smaller than 1 over the string length. Now, the other bound we obtained by thinking about the rate of emission and how the entropy changes with that. So if we are at temperature T, then a quantum is emitted every thermal time 1 over T. And now we have to look at the loss of entropy when that happens in that time interval that we're looking at. And the change of entropy is proportional to the time interval times T, times the temperature. And we want that to be small. So smaller, the change should be much smaller than the entropy. And that gives us a second bound on the rate of change, which is given by the temperature over the entropy. And at the correspondence point, the temperature is given by 1 over the string length. And so this gives us the bound 1 over the entropy times the string length. Now, because the entropy is large, there's ample room to satisfy both these bounds and to be within this sort of Goldilocks adiabaticity regime. But one thing is important to keep in mind is that for finite entropy, so when you're not going to infinite entropy, you never have an exactly adiabatic transition. So once we're away from supersymmetry, we really have to look at time frames because things evolve and we never have exactly stable objects. And this is the regime in which we should be talking about black holes and strings transitioning into each other. Now, let's say the last two things that I'm going to say before we can take a break is the physical realization. So I said before that we can tune the coupling by tuning the dilaton. And we want to do this in such a way that we have the entropy stay fixed. And we also want to be within this Goldilocks adiabaticity range in order that we can say that there's a transition between black holes and strings. And so what we're going to imagine is that there's a dilaton wave that we send through our system. And as we increase or decrease the value of the dilaton, the black hole can transit, well, the object is described by a string or the object is described by a black hole. Now, there's another way in which the string black hole correspondence emerges in sort of a physical realization. And this is when the black hole evaporates. Now what we're doing is not keeping the entropy fixed, because obviously the black hole will radiate away its mass and therefore the entropy will go down. But we're going to keep the coupling fixed. We're going to stay within the same theory and we're going to look at the black hole as it evolves. Keeping the coupling fixed, the entropy changes and therefore also the mass changes. So the mass decreases as the black hole emits Hawking radiation. And it's natural to expect that near the endpoint of such an evaporation, when the black hole has shrunk down to string size, a description in terms of a string will take over. Unlike with the dilaton wave, we don't get to choose the transition rate between black hole and string. So we have less control in this scenario. But when the string coupling is small, then the evolution can be slow enough so that we can talk about the transition. And since we have an entropy that is large, and the loss of entropy through radiation is much smaller than that number, we can still talk about an almost adiabatic evolution if the transition happens during a few string units of time. So this is another way in which we can talk about black hole string, a transition in a physical realization. So to summarize that first part, I explained how black holes and fundamental strings can be thought of as the same system by changing the coupling and having their properties match at the correspondence point, where the string picture gives a statistical interpretation for black hole entropy. I want to emphasize again that since we're away from supersymmetry, we do not have an exact counting of the entropy. So we don't get the order 1 numbers out, but it is a parametric matching that is still highly non-trivial. I just talked about physical realization in evaporation or by sending a dilaton wave. And the statement here there is that this picture, unlike the very specific BPS black hole string relations, applies to generic black holes in general dimensions. Generic up to the fact that I have just discussed static black holes until now. And after the break, I will update this statement to completely general black holes that can also rotate and in arbitrary dimensions. Okay, shall we take a break now? Okay, so before the break, we ended with this summary of the correspondence between black holes and strings without rotation. And I've highlighted that this furnishes a statistical interpretation of black hole entropy, at least at the correspondence point. And I'm going to discuss some limitations, which, as I already mentioned before, since we don't have powerful control as we have with supersymmetry, the matching between fundamental string and black hole properties can only be parametric. And it also only happens at one value of the coupling, namely when G square S is of order 1, which is where the two pictures collide. I also took some time in talking about the kind of transition that we're looking at, where we need an approximate notion of adiabaticity. So we need to look at this regime and compare that to the evolution of the string and the black holes through dynamics. And then the third limitation is that here I have not talked about self-gravity much, other than mentioning that it makes the sizes agree. So this is another important ingredient that we will have to keep in mind. But for what I'm going to tell you now, we're going to ignore this aspect and see how well we can do without including self-gravity. So now we're going to add rotation, and rotation will add qualitatively new features. So this is the second part. So first of all, let me point out that once we are in general number of space-time dimensions and we add rotation, there's actually a zoo of black hole and string-like objects. And it will be very useful to characterize them by looking at two different length scales. One we'll call the mass length, which is given by Newton's constant times the mass to some power that contains the space-time dimension. And the other is what I'll call the spin length, which is given by the angular momentum divided by the mass. When we're in the regime where the spin length is smaller than the mass length, then the objects that we're looking at on the black hole side are unique, roundish, and they are dynamically stable. And this is what I will refer to as the Kerr regime. So in 4 dimensions, this really relates to sort of the Kerr bound, but in higher dimensions, I will still continue to call this the Kerr regime up to the bound where the spin and the mass lengths are saturated. The other regime is where the spin length is bigger than the mass length. And then on the black hole-ish side, we can have now different shapes of black holes, but also different topologies. For example, we can also have black rings or other kinds of objects. And they are dynamically unstable. And I will refer to this regime as the ultra-spinning regime. Now on the string side, string are also unique, roundish, and dynamically stable when we are in this Kerr regime. And there are also kind of different shapes and topologies or different shapes of the string and interesting dynamics when we look at strings in the ultra-spinning regime. And then there's also very recent constructions of objects that include kind of both components. They're like black hole components, including strings that stick out of the black hole. These are kind of hybrid solutions which have been constructed last year and which will be important in the black hole string correspondence with rotation. So what we're going to do in the following is we're going to discuss these two objects and we're going to discuss them in terms of the adiabatic invariance, entropy, and spin. Now let's get back to these puzzles that I raised before. So on the one hand, for black holes, we have the Kerr bound. For strings, we have the Regge bound. And we learned before that when we express them in the same units, we see that the Kerr bound is much smaller than the Regge bound. So what this means is that on the string side, we can have strings all the way up to the Regge bound. They will start out roundish and then will become more and more elongated because instead of doing random walks, the oscillators now have to help the string get angular momentum. And there's less oscillators available to make it sort of give it a degeneracy and make it look roundish. On the black hole side, in 4 dimensions, we only have black holes up until the Kerr bound, and beyond that, there seems to be no black hole counterpart to these highly spinning strings. And that's the first puzzle. Now let's move on to higher dimensions. So dimension 5 and higher. We just learned that beyond the Kerr bound, or the Kerr type bound, we can have other kinds of objects that are highly spinning, other kinds of black holes or black ring type objects. And they can exist in principle with arbitrary spin. On the other hand, on the string side, the strings exist until the Regge bound and nothing beyond. And so the second puzzle is that we have ultra-spinning black holes in high dimensions, but there don't seem to be any stringy counterparts. Okay, let me gloss over that. So now we want to resolve these two puzzles. And I anticipated before that there is actually an assumption hidden in there. And the assumption is that we try to match stationary string to stationary black hole solutions. But we have just learned that when we are at finite coupling, so away from zero infinite coupling, all objects time evolve. And we have to keep that, take that into account. Now, when we add rotation, this Goldilocks adiabaticity regime becomes very important. And it turns out to only be satisfied by some states, but not all. And that will be part of the resolution. So we can resolve these two puzzles. That in 4 dimensions, there are no black holes beyond the Kerr bound that would transition into strings, and that in higher dimensions, there are no strings that would match onto these ultra-spinning black objects. And these puzzles can be resolved by correctly accounting for the dynamics. So let's look at the dynamics now. So we have these two regimes, the Kerr regime and the ultra-spinning regime. Now in the Kerr regime, things are classically stable. So we don't have to say anything more. In the ultra-spinning regime, however, interesting dynamics happens. And so black holes and black rings are actually unstable in this regime. There are bar instabilities. So when we have black holes that are shaped, because they spin so much, they're shaped like bars, they're deformed. And then if we have highly elongated objects, for example, if you look at the black ring, and you have perturbations on the horizon of that object, then there can be instabilities towards what is known as gregular flamme, which once this object pinch off. So we can either have death by radiation through these bar instabilities, where they rotate very fast and they emit radiation, or we can have death by fragmentation, where we have like elongated objects with some ripples, and then there is an instability towards fragmentation. Then we also have these hybrids enter the picture, and we can have so we have spinning objects that contain both a black hole component and a string component that sticks out of the black hole. It can be entropically favored that the entropy of the object is carried by an almost static black hole at the center, and then the rotation is carried by a string that stretches out a lot and gives it its large angular momentum. Now, if these objects are not stable, they will actually radiate away angular momentum and turn back into a regime where we have a sort of roundish black hole. But we have to look at the transition timescale of that process. So having these hybrids allows for kind of stage correspondence. If we start with a string that is highly spinning, then we could have a transition into a black hole part of this object near the center. So when we are looking at a black hole, the curvature of the horizon can become stringy first, and we still have some string components sticking out of the black hole there's a rounded string object where there's some string components that give angular momentum. And as we increase the coupling, the roundish part becomes a black hole first and the string still sticks out. So this is a way of having a stage correspondence where part of the object, part of the string object becomes a black hole first and vice versa. Okay, so now this includes the important components that are necessary in order to talk about the black hole string correspondence with rotation. Are there any questions? Okay, if not, then I'm gonna tell you now what happens when we add rotation. So here is the diagram that depicts the coupling squared over angular momentum. The blue line is where we have the bound between the Kerr regime on the one side and the ultra spinning regime on the other side. And the red line separates the string from the black hole regime. So strings below, black holes above. So let's talk first about the transition from strings to black holes. And let's do that in general space-time dimensions, because on the string side, there's no difference. So below the Kerr-like bound, we have roundish strings. Above that bound, we have these highly spinning strings that look more like rods. How do they transition into a black hole? Well, the roundish strings just becomes a roundish black hole. The elongated, highly spinning string transitions into either one of these hybrid objects where we have the center of the string, which is given by oscillators that give the entropy, first becoming a black hole, while the angular momentum part, given by a highly rotating string component, still remains a string. So these are these hybrid objects. Or we can also have the object during the transition shed some of its angular momentum and actually turn into some bar-like black hole objects. So we have established that in higher dimensions, there are black hole objects beyond the Kerr bound. And we even have unstable objects in 4 dimensions. So this is the way of how we can resolve the first puzzle. If we start to include objects that are not stationary, then we can make sense of a string going into the black hole regime for all values of the angular momentum. Now what happens when we go from black holes to strings. So in 4 dimensions, we may only be interested in the black holes that exist below the Kerr bound anyway, and they transition into roundish strings. So no surprise there. But then in higher dimensions, the Kerr bound is not an existence bound, it's more a stability bound, and we can have objects beyond that that are unstable. First, the roundish black hole again becomes a roundish string in any dimensions. But then in high dimensions, we have these other objects with different shapes and topologies that exist in the ultra spinning regime. And what happens to those objects? So here it is important to first to look at the timescales and to compare the instability timescale to this Goldilocks adiabaticity regime within which we can transition between black holes and strings. So what happens for these highly spinning objects is that first the instability kicks in. So we can have highly spinning black holes that turn into bar-shaped objects or objects with a string component, or we can have these objects that undergo a Greger-Laflamme fragmentation instability and become multi-component black objects. And then the end products of these decay either by radiation or by fragmentation, it's those end products that can then transition into a string in an almost adiabatic sense. So for example, the multi-black hole object will become a multi-string object. And so this shows that in order to make sense of the black hole string correspondence with general angular momentum, we need to include not just single string states, as I've done before in the static case, but we also need to include multi-string states. So this resolves the second puzzle. These ultra-spinning objects are unstable and they first decay before they can transition, and then the end products is what are the black hole counterparts of the highly spinning strings. Okay, are there any questions on the correspondence in general? So when you have supersymmetry and you are in the realm where we understand really what, as you make the coupling smaller and you come into this regime where you know what the bound states of strings or branes is, then you can compute quantities that remain the same across changing the coupling. So this is what we call index, right? And the degeneracy of states is such a number. But here we have no supersymmetry whatsoever. We would like to understand the entropy of a black hole in the sky. There is no supersymmetry. There is no anti-de Sitter near horizon geometry that allows us to use the ADS-CFT correspondence. So these are, objects that are very hard to understand. They're very simple in GR, but they're very complicated as far as microscopic description is concerned. And here we're trying to understand them by objects in a theory beyond general relativity that includes quantum effects and gravity in a consistent way. And we're looking at the simplest possible object in the theory, a highly excited string state. And we're trying to make a connection between these general black holes in arbitrary number of dimensions with arbitrary angular momentum, and on the other hand, a highly excited string state. And since there's no supersymmetry, we cannot expect numbers like this 1/4 in the black hole entropy to match. But what we can hope to match is parametrically how things go. And so like the mass, the decay rates, and the sizes, what I discussed before, is something that should match at the correspondence point once you have declared that you fix the entropy. So this is maybe, it's a bit unfamiliar to fix the entropy. It's sort of, we're looking at an ensemble with fixed entropy that may be a bit unfamiliar, but it is really the analog of what we're doing when we're in a situation with supersymmetry. There we have an understanding of the microscopic ingredients because the entropy and various other things stay the same, or we have control over how they change as we change the coupling, like the mass. So there are things that are under control because of supersymmetry. And the entropy of the string really is given by this number of branes. And so that's why we describe everything in terms of fixing the number of branes and then stating how properties of black hole and this D-brane system are equal. But here we don't have that n. We have only the entropy to work with. And so the most natural extension from this BPS scenario, where we understand things really well, is to say, well, instead of fixing the number of branes, we don't have them. We don't know what microscopic degrees of freedom in terms of branes are, but we can fix the entropy, and then we can see if we can map black hole physics to stringy physics using the simplest object in string theory, which is a string itself. Then on top of that, there can be much more refinement, as relating to the question that you had before. There can be much more refinement, but we are sort of starting with the first layer. We are trying to set the stage of what are the rough. It's like a broad brush picture that we are drawing here, and then there's like much more finer details that you can put on top. Here I'm still doing broad brush physics.
Okay, thank you.
So another broad brush matching will be to understand how the sizes of black holes and strings in the setting with no supersymmetry and with rotation are. So I told you before that for static black holes and static strings, if you don't include the effect of self-gravitation, then the sizes don't match. The string is much more fluffy, and the black hole at the correspondence point has string size, so it's smaller, and so they don't match. But once you include self-gravity, the string becomes more compact, and the two can actually match. Now I'm gonna talk about sizes and shapes of black holes and strings when you have rotation. And this is actually based on work that is just about to appear. And it's also based on earlier works. Some of them I mentioned, well, I mentioned both of them in the literature in the beginning. So there were some works by Mitchell and Turok in '87 that looked at the size of static strings. And we're doing the sort of natural generalization of that to rotating strings. And also what goes into this computation is the degeneracy of states, which I have discussed before for the case of static strings. And this has been extended in the mid-90s by Russo and Susskind to highly spinning strings. So these are the two kinds of results that we base our work on sizes and shapes of generically rotating strings on. Okay, so what happens when we spin up a black hole? Well, if we start with a roundish black hole with no rotation and we spin it up, well, it gets squeezed, right? So there's a centrifugal effect of rotation that counteracts the gravitational attraction. And then the region that is trapped gets smaller. It reduces the size of the event horizon, and it gets squeezed in the along the axis of rotation. Now, a black hole with mass m, you can think of it consisting of two components. One is heat given by the temperature times the entropy, and the other is mechanical energy. If you increase the rotation, then for a given energy budget, this decreases the heat fraction. And so the geometrical counterpart for heat, which is the horizon area, because it comes from the entropy of a black hole. And then the overall size of a black hole of mass m must be smaller if you have larger J. So the size gets smaller and for a given mass of the black hole, and it gets squeezed. It gets stretched along the plane of rotation, and it gets squeezed along the rotation axis or perpendicular to the plane of rotation. So this is what happens for a black hole. And this can be seen by an explicit formula that one can write down for black holes whose spin, whose angular momentum J, is smaller or of the order of its entropy. And one thing to notice here in this expression is that the angular momentum shows up as a square and in combinations with the entropy squared. And we'll get back to that in a moment. Now, what happens when you spin up a string? Well, a similar picture to what I've just told you for black holes holds for a string as well. In a typical massive string state, the oscillator excitations come in two classes. So there's one where the string is made to coherently rotate. So you give some of the oscillators you put them up in such a way that they give you coherent rotation. And then there's the class of oscillators that just does the random walk thing. So it just makes the strings jitter, and this is where the large degeneracy comes from. Now, if more oscillator energy is used for rotation, then less is available for random walk. But because the size of a random walk grows with the square root of the number of random steps, you can then see that if you increase the total angular momentum, it reduces the overall size of the string ball. And you again expect that the size gets increased in the plane of rotation and gets decreased perpendicular to it. And we can update the formula that we have discussed for static strings that relates the string entropy and the string mass. Now, in addition, including angular momentum. And this formula holds for when the angular momentum is of the order of the entropy. Now, these two formulas that I've shown you hold in different regimes. One was much smaller than the entropy, one is of the order of the entropy, so you cannot really directly compare them. But what do we expect? So what I would like to compute in the following is I would like to choose one rotation plane for black holes and for strings. And then I want to compute the size of the object in that plane and perpendicular to it. What we expect from on the black hole side from this formula that I've shown you before is that the ratio between the perpendicular size and the parallel size, so perpendicular to the plane of rotation and in or parallel to the plane of rotation, that size is governed by the angular momentum squared over the entropy squared. So that's sort of the functional dependence of the angular momentum that we expect for black holes. And we will see that in the regime where the angular momentum is much smaller than the entropy, that this relation also bears out for strings. And in being so, this provides a new, extra evidence that the correspondence between black holes and string works in the presence of rotation. Now, what do we expect for large spins? Well, for large spins, we expect the black hole to really pancake, be much larger in the plane of rotation than perpendicular. We expect a similar effect for strings too. But we also know that at large spin, I just explained that large spin, there's all these dynamics going on, all these decay channels. So we do not actually expect the string and the black hole with very large amount of angular momentum. We don't expect them to match. And so we also don't expect that when we compute the sizes in and transverse to the rotation plane, we don't expect the sizes to match. And we're going to see that as well. Okay, so let's get to it. So we discussed before how to get the degeneracy of string states when they're static. So let me just review those expressions. So from the level counting operator, we can get the Hamiltonian. We can write down a partition function. We've computed that before. In particular, in the thermodynamic limit, where the temperature is high or this inverse temperature beta is very small, there's an explicit formula for this infinite sum, which in particular says that the partition function has an exponential in 1 over this inverse temperature with some prefactor. And then the density of states is obtained by extracting this coefficient dn from a saddle point approximation at large oscillator level n. And we saw that the leading order term is this exponential in the square root of n. So that square root of n was the entropy. Now what we want to do is we want to sort of do a similar computation, but not extracting the density of states, but extracting the size of the string. So before I gave you the expression for describing the transverse components of the string xi. Now what's the size? The size is roughly speaking xi squared. And in terms of the oscillators, that's this infinite sum over 1 over n squared, and then these oscillators alpha n and alpha minus n in the transverse directions. So we want to compute the expectation value of this xi squared, or let me call it r squared for short. And then the analog story to extracting the density of states is to extract this coefficient rn squared. And for static strings, this has been done by Mitchell and Turok, who found that this coefficient Rn squared is given by square root times n, so the entropy, times the density of states at level n, dn. And the result that they got then for the average size of a string, which is given by this coefficient Rn squared upon dividing by the density of states, is just square root n. And square root n is just perfectly matches the size that you would get by a very simple random walk model. The random walk model tells you that you get square root n, that is proportional to the mass, it's proportional to the length, so to the random walk length. So that's that bears out perfectly. Now we want to do this for rotating strings. So for rotating strings, we have to introduce a way in which we add angular momentum to the string. And the natural way to do this is to choose a rotation plane. Let's say the plane 1, 2. So that those are the spatial directions 1 and 2. And we're gonna pick these oscillators in those directions, so alpha 1 and alpha 2. And we give angular momentum to the system by picking this particular combination of oscillators that I've written in red. So that changes then our static Hamiltonian to something where we add a term minus angular velocity times angular momentum. And the angular momentum is carried by these oscillators 1 and 2. Now let's compute the partition function from this in a similar way as in the static case, but now we have, instead of a power d to the minus 2 on that expression, we have taken out 2 of these factors because we have these 2 directions, 1 and 2, in which we also have rotation. So the d minus 4 directions are just random walk oscillators, while we picked out 2 directions, the 1 and 2, to make the spin, the string spin. And this will give this extra factor in the partition function, which has an e to the minus beta n plus omega and e to the minus beta n minus omega terms. And now we have to evaluate that infinite product. In the thermodynamic limit, that computation again simplifies. So what is in gray is the partition function in that limit for static strings. And the red part, this omega over sinh pi omega, is what you get in the presence of rotation, as given to the string by angular momentum in these oscillators. Now we need the density of states of rotating strings. So again, we write down this infinite sum of e to the minus beta n with some coefficient. And now since we have rotation, there's also an e to the beta omega j, and the coefficient, the density of states will now depend also on j. So we want to extract from this infinite sum the coefficient d and j, which is the degeneracy of string states at excitation level n and fixed angular momentum j. So this computation was done for large values of j by Russo-Susskind, as I mentioned before. And we want to extend this computation to arbitrary values of angular momentum, because we are in particular interested in the regime where the angular momentum is very small and where we expect a good matching to black holes. Now we also want to compute the size of rotating strings. So again, we want to compute the string position xi squared, given in terms of these oscillators. But now we have rotation, so we're going to extract a coefficient rnj squared. Here we have chosen just one rotation plane. And so we have 2 types of sizes to compute. One is transverse to the plane of rotation, and one is in the plane of rotation. And so from these coefficients that we're going to extract again in some kind of saddle point approximation from this average r squared computation, this is what will tell us how large the string is in those 2 directions. So in the following, I'm going to compute the density of states for strings at level n and j and the corresponding parallel and transverse sizes of the string. And then we're going to check how they compare to the black hole sizes. Okay, so let's start again with this partition function. Now a term in the angular velocity and angular momentum added to it. In the thermodynamic limit, that's the simple expression. And now we have to work a little harder compared to the static case because of this extra factor of omega over sinh pi omega. So the density of states, as I described before, is extracted from some saddle point approximation of some integral. So this is the integral here. This is how you extract the density of states from this infinite sum. First, we want to, at the end of the day, we want to compute that at some fixed angular momentum. So we have to get rid of the angular velocity and turn it into angular momentum. And this is done by some integral transform. It's a Fourier transform here that takes the angular velocity and replaces it by j. So that integral can actually be done exactly. And it spits out something that depends just on the absolute value of angular momentum. Now you plug that into the density of states. Then you go to large n, which is the excitation level, which is the dominant contribution to this sum. And you get a condition for the saddle point of this integral that has to be satisfied. And from the solution for beta of this saddle point equation, you can extract the saddle point and then plug that back into the density of states integral and get out the degeneracy. So we can do this easily by approximating this hyperbolic tangent by 3 values. So we can solve this equation very easily when beta times the absolute value of j is either 0, some finite number, or infinity. And that simplifies this hyperbolic tangent to being given by either 0, 1, or some number in between. And it turns out that these 3 different values in which we can solve this easily matches with 3 different scalings of the angular momentum that we are interested in. One is where the angular momentum is of order 1 compared to the entropy, so it doesn't scale with the entropy, which for the string is given by square root n. So this doesn't scale with the entropy, then we are interested in large angular momentum, meaning that j scales of order n. Or we are also interested in regimes in between, where we have some moderate spin. We want to see if there's a matching between strings and rotating black holes with moderate spin. Okay, so you can do this computation, figure out what the saddle point is, then plug this back in, and out you get some rather horribly looking expression, which we use as an input for the size computation. So never mind the details here. These are 3 regimes in which we can compute things, and this is where we want to compare the sizes. Okay, so let's compute the sizes. So first we want to look at the size of the string perpendicular to the plane of rotation. So this is this R perp, from which we extract this coefficient Rn perp squared. Now it turns out that this this expectation value of R perp squared can be easily expressed in terms of the partition function of a rotating string times the log of the partition function for a static string. So that's just what it is. And so we see that up to subleading corrections, which are given by this log, the result of this computation extracting the coefficient here is the same as for the density of states, because this is just an extra. So for the density of states, we just had the partition function for the rotating string, and now we have this extra logarithmic factor. So the steps are very much the same, except for logarithmic correction. And at the end of the day, you can compute the coefficient of this expectation value of the perpendicular size. Again, the details won't matter too much. I just put them here because we can do this explicitly, and I will now discuss in the end the key physical features. So the other thing to compute is the size in the plane of rotation, and this is a much more complicated situation. This expectation value R parallel squared is again given in terms of the partition function of the rotating string. But now it also contains another infinite sum, which is denoted by rho, which depends still on the angular velocity. And this is complicated. Again, when you go into the thermodynamic limit, this object, which we call the rotation function, simplifies. And it's just given by this ratio 1 minus pi omega cotangent pi omega over omega squared. So it adds another factor in terms of the angular velocity, which you need in order to compute this parallel size. Okay, at the end of the day, again, we do a Fourier transform to go from angular velocity to angular momentum. That can be done exactly. There's again a saddle point equation that you have to obey, and I'm just showing this because it highlights how sizes are much more complicated than density of states. At the end of the day, you can do a similar analysis as before, where you approximate this in 3 regimes. Those are the 3 regimes we care about: angular momentum being of order 1, of order n, and of order square root n. And at the end of the day, you get some, again, horribly looking expression. Okay, so what's the point of all this? Let me now summarize this: the average sizes of string states transverse to the rotation plane and along the rotation plane. So when the spin is very small, to leading order, the sizes are just given by square root n. So angular momentum doesn't show up if we are working at leading order in the large n expansion. At large values of the angular momentum, we see a difference between a strong difference between the size in the plane of rotation and perpendicular to it. In transverse to the plane of rotation, the size compared to the static case just shrinks depending on the value of the angular momentum. So in the static case, it was just square root n. and now it is square root n minus j. However, along the plane of rotation, the size is just j. And so if your j is very large, then the string spreads quite a bit in the plane of rotation. And then for more moderate string sizes, the angular momenta make the spin squeeze a bit in the perpendicular direction and elongate it a bit in the plane of rotation. But the effect is not as strong. Now, do we actually expect the individual sizes in these two directions to match between black holes and strings? We don't, because sizes are not adiabatic invariants, unlike the entropy. So we actually expect that the sizes significantly change with the strength of the interaction. So why I've been telling you about these sizes when we don't expect them to actually match? Well, there is a combination of these two sizes that we do expect to match. So if we take the ratio of the sizes in these two directions, then this ratio varies much less with the coupling. And so therefore, we expect it to be approximately adiabatic, so an approximate adiabatic invariant. And this is why we expect it to potentially match onto black holes. So finally, the bottom line of these computations that I've gone through with you in detail are that if you take the ratio of transverse size to the size in the rotation plane, this is the thing that we want to compare. So at leading order, which is what we have been working with, leading order at large excitation level, for small rotation, this ratio is of order 1, like it was in the static case. For moderate rotation, it's given by some constant, which is smaller than 1. So that means that the string gets squeezed a bit in the direction orthogonal to the plane and gets stretched a bit in the direction of the rotation. And then for large spin, it's given by the entropy over angular momentum. That's just what it is. Now we want to compare this to the corresponding expressions for black holes. But before that, let me introduce subleading corrections, because for moderate angular momentum, this ratio being 1 was not very exciting, because it just meant that everything was like in a static case. We can do a bit better in that situation and add subleading corrections in large N. And these subleading corrections highlighted above in red have various terms. And you notice that there's a subtle cancellation between terms that don't depend on the angular momentum, such that these terms cancel out. And in the ratio, there's only a term that is proportional to j square over s square that survives. And this is significant because the other terms, they're just not there. Okay, so let's keep that in mind. We have something of order j square over s square for small spin, and some constant smaller than 1 for moderate spin, and then something much, much larger, s over j, in the case of large spin. Let's compare what happens for black holes. So for black holes, and we can take some general black hole in high dimensions, like the Myers-Perry black hole, and look now again at some suitable defined perpendicular and parallel size. There are two natural quantities that we're going to work with. So for the perpendicular size, we're going to define it as the transverse characteristic radius at the pole when the azimuthal angle is 0 on the horizon. And this expression, well, it's just the horizon radius. For the direction in the rotation plane, it's less clear what is a natural choice here for defining that radius when we have angular momentum. But what we're going to do is we're going to pick the simplest definition that is also natural. And so we define it in terms of we define the characteristic radius in the rotation plane by the horizon area in the angular directions. And this is given by the square root of horizon radius squared plus this spin length squared. And we're going to take these two definitions of perpendicular and transverse sizes, compute them for the different scalings of the angular momentum, and then compare it to the string. So we can write them down in general dimensions in an explicit way in terms of the mass, the spin, and the angular momentum. The thing that is adiabatic invariant is the entropy and the spin, but not the mass. So similarly to the string, these two individual sizes will change as we vary the coupling because the mass changes. But the ratio again has the mass drop out, and so we again have a sort of approximate adiabatic invariant in terms of S and J. So what is the ratio here? Well, we have something that is 1 minus some expression that is J square over S square for small spin, small compared to the entropy, some constant that's smaller than 1 for moderate spin, and then something that is S square over J square for large spin. Again, we see that there is a pancake effect if the spin is very large. And otherwise, this is the functional dependence in terms of J. So let's compare the two, black holes and strings. So on the left, we have the string sizes. On the right, we have the black hole sizes. And you immediately notice that for small J, we get this functional dependence on J square over S square, and not any other dependence on J, and also not any other dependence on S. And this is the leading correction dependent on J for both strings and black holes. And so this is a very nice match between rotating black holes and strings for an approximate adiabatic given by these size ratios. Then you notice that for more moderate spin, both of them are given by some order 1 number that's smaller than 1. So there's also a rough match between black holes and strings. And then for large spin, you notice that, well, the two are very different. One is the square of the other. But this is no surprise because we already established that for highly spinning black holes and strings, there's no direct correspondence because there's first some dynamics that kicks in that makes the black objects decay, and only the decay products can match onto strings. And so this mismatch is actually expected. Okay, so for small angular momentum, we get a perfect match up to the order 1 number, which I have mentioned a couple of times. We cannot expect to match. For moderate spin, there's also a heuristic match. And then for large spin, there is no match because we don't expect it. Okay, so this brings me to the summary. So I've discussed how to extend the correspondence between black holes and strings in the presence of rotation. As you approach the correspondence point, properties of the objects agree. We have fixed the entropy, so the other properties like masses and decay rates and so on have to agree. And we have added to this discussion the computation of the sizes of both objects, and we see that they also agree. So in the presence of rotations, we have these new elements that are dynamical factors. Black holes are unstable. They can emit radiation or fragment. We also have to include different phases into this picture. We have to allow for these black bars, black hole string hybrids. We even have to include multi-string states. And we have computed the sizes from which you can also infer to some extent the shapes of strings and black holes. And we saw that they further support this picture of a correspondence between black holes that rotate and rotating strings. Thank you very much, and I'm happy to take questions now.